Okay, maybe that was too much theory, and now we should discuss some examples, right? So let's discuss some examples. We're going to start with the simplest possible example, meaning that we're going to start with the simplest possible measure. What's the simplest possible measure? Dirac. What does that mean? So let's fix some arbitrary measurable space and pick mu as Dirac at a fixed point. So this is a fixed point in omega. And recall that Dirac was defined as 1 or 0. So 1 if omega 0 is in your set, 0 if omega 0 is not in your set. So the picture was very nice. So there is a fixed point here with a 1 kilogram of mass. So the question is, do you cover it in your set or not? So now what is xd mu? xd Dirac. So what is this? Well, let's start with the step 1, okay? So step 1 or step A, whatever. So if x is the indicator of a set, so indicator A, d Dirac, okay, will be the Dirac measure at A. Okay, so this is 1 if omega 0 is in A. Okay, what does that mean? Omega 0 is in A. What can you say about the value of x? Omega 0 is in A. Can you say anything about the value of this indicator function at omega 0? Well, yes, it is 1. Otherwise, it is 0. So these two expressions are precisely the same thing. In this, you have a measure. Your argument is a set. In this, you have a measurable function. Your argument is a point. So this is x of omega 0. So the integral gave you nothing but the value of the function at that fixed point. Because the measure is just concentrated on that fixed point. Therefore, the integral can just be about this fixed point, right? And you simply evaluate your function, your random variable, at that fixed point. That's what the integration with respect to Dirac measure does. Well, you can write it as, you can generalize your result. Let's say x is A1, indicator A1, to AM, indicator AM. In that case, x, the Dirac, will be what? It's going to be A1 Dirac at A1, AM Dirac at AM. And this is simply equal to the indicator of A1 at omega 0, indicator of AM at omega 0. Therefore, this is equal to x of omega 0 again. Take x positive measurable and x1, x2 increasing to x that are simple. So what do we have? In each of the simple functions, we have xn at omega 0, right? Mu is Dirac. So by the previous step, for each of the simple functions, you're just going to evaluate your function at omega 0. Therefore, the integral of x will be the limit of integrals of xn's. And each of those integrals is equal to xn of omega 0. And since xn's converge to x, you again get the same result. Finally, if you have x, which is just arbitrary, like x plus minus x minus, In that case, you have integral of x equals x plus minus integral of x minus. So this is equal to x plus at omega 0. This is equal to x minus at omega 0. Therefore, this is equal to x of omega 0. So conclusion, Dirac measure, when you integrate a function with respect to the Dirac measure, all you're doing is to evaluate your function at that fixed point of the measure. So we had no idea about the exact value of this integral. So we started with simple functions, indicator functions, and we saw something. And this really looks like a general result, okay? Because at the end of the day, our measure is very simple, just Dirac. So therefore, we aim to extend it to the most general setting. So we followed our usual path, indicators to simple functions to positive functions, and positive functions to general functions. Of course, always we have measurability. Okay. Now, second example is the generalization of Dirac, which is the discrete measures, right? So instead of having just one fixed point, you can have countably many fixed points. So again, you have omega f, and you have now a set of fixed points. Let's say d, omega 1, omega 2, set of fixed points in omega. And to each of them, you have a mass, m1 kilograms, m2 kilograms, etc. etc. So our measure is now this. At any set, it is, let's say, 1 to infinity. You can study the finite version of this as well. So it's not just one Dirac measure, but multiple Dirac measures. And you can have a weight that is different from 1. So these are positive weights, just to make sure it is a measure, it's positive valued. Again, in that case, for instance, if you look at indicator of a set A, the integral of x with respect to mu, this mu, will be what? It's going to be just mu of A, right? And this is equal to mi Dirac omega I at A. But Dirac is equal to also the indicator function at this point. Therefore, it is mi x at omega I. So what you do is to evaluate your function at each of the points and multiply it by its weight, by its mass. So it's generalizing what the Dirac measure is doing, because it is now a discrete measure. Whereas this was the Dirac measure. So you can check for simple, positive, and general functions that x d mu gives you mi x at omega I. So again, all we are doing is to look at the points on which mu is concentrated. So mu is concentrated on those points, right? So what you do when you integrate a function with respect to this kind of a measure is to look at the values of your function at each of those points and multiply that value by its assigned mass. Well, general functions can be problematic. Let's avoid general functions. Let's stop at positive functions. Why? Because you might have some infinity minus infinity issues. If you allow for general functions, that's an infinite sum. You can get some not very nice results. So let's avoid general functions. Let's stop at positive functions, okay? Just to avoid infinity minus infinity. And one special case of this is when omega is countable. And F is just the power set, the discrete sigma algebra. In that case, every mu on omega F is a discrete measure. So if omega is equal to omega 1, omega 2, etc., and the mu assigned to omega I is mi, okay, then by 2 we have x d mu equals mi x of omega I for all x positive. And they are always measurable because you picked F to be the power set, so everything is measurable. No, omega is just a countable set. It's a discrete space. Okay? So it's automatically partitioned into its singletons, right? Singletons partition it. So it's a special case of number 2. In number 2, you have an arbitrary measurable space where you have some fixed points with assigned masses. Here you have just a countable set. Therefore, you can see every point as a fixed point, like here. And the probability or the measure assigned to this singleton is like a mass assigned to this point. So therefore, every measure on such a space, a countable set, omega, every measure on such an omega is a discrete measure of this form. So maybe these examples are too discrete, and then we should discuss a continuous example. Okay? Let's say omega is R, or let's say a Borel subset of R. Okay? Okay? For instance, let's say omega is A to B interval. Okay? So F is the Borel sigma algebra on omega. You know how to define it, right? You have the Borel sigma algebra on R. And if you need a Borel sigma algebra on A to B, you trace the full Borel sigma algebra to A to B. Right? You trace your big sigma algebra to the smaller set. And mu is the Lebesgue measure. Remember the Lebesgue measure. It measures length, right? Just length. So since we're on the real line, our measure space is the real line, I'd like to denote a measurable function by f, not x, okay? Like in classical calculus or classical analysis, right? So f is a function on omega to r. Let's say it's bounded and measurable. Let me write it in full. And let's even suppose omega is just a to b, okay? So we have a function like this. A here, b here. Something like this. What does this remind you from calculus? What kind of an integral did you learn in calculus? What is the name of the integral in calculus? Riemann integral, right? So you remember Riemann integrals. How was that defined? Well, what you do is to partition your interval like this. Okay, let's say this is A1, A2, A3, A4, A5, and this is A6. What you do is to look at the minimum value of the function in each of those intervals. So the maximum value of the function on each of those intervals in your partition. Okay? So you can calculate this blue region, the area of the blue region, as a sum of areas of rectangles, right? So this is called a lower Riemann sum for f with respect to partition pi. What is partition pi? Well, partition pi consists of A1, A2, up to A6 in this picture. Lower Riemann sum. I'm not going to write it in the full formal way, but you can also calculate upper Riemann sums if you also calculate the areas of the rectangles using the maximum values. Since your function is bounded, you can find such an upper bound, the maximum value. And now this is called the upper Riemann sum. Now, we say f is called Riemann integrable if the largest possible lower Riemann sum that you can obtain using the set of all partitions, all finite partitions, I should say, of A to B, is equal to the lowest possible upper bound that you can get by the upper Riemann sums. And in this case, this value is called the Riemann integral, denoted as a to b f of x dx. What is very nice is that if f is Riemann integrable, then, and it is even if and only if, the set of all points at which f is discontinuous at x has Lebesgue measure 0. Of course, we're not going to prove it, but that's a very nice characterization of Riemann integrability. So apparently there is some connection between Riemann integral and the Lebesgue measure. And in fact, there is a connection between the Riemann integral and the Lebesgue integral. The reason is can somehow be seen on the picture. Well, you see, this is like the integral of a simple function, right? If you look at this lower Riemann sum, you're just calculating areas of rectangles, right? So like this value times the measure of this interval, Lebesgue measure of this interval, this value times the Lebesgue measure of this interval, et cetera, et cetera. So this is like the integral of a simple function. And also for the upper Riemann sums, they are also like Lebesgue integrals of simple functions. So the connection is that if f is Riemann integrable, it is also Lebesgue integrable. And the two integrals coincide. So we use f dx, d Lebesgue for the Riemann integral. So I put the full space here. And a to b, the standard calculus notation, is for the Riemann integral. So this is a nice connection between Riemann and Lebesgue integrals. We just state it as a fact, but we're going to use it a lot. This is, in fact, the bridge to reality, right? Reality meaning that practical things, things that we can calculate. So we're going to calculate expectations, covariances, distributions, a lot of stuff, right? So that's the bridge to real world. So far it was all abstract mathematics, but the next step will be to actually sit down and calculate some values. This is going to happen next week when we learn distributions. But the idea will be to somehow pass to the Lebesgue, the integral with respect to the Lebesgue measure, so that we have a connection to the Riemann integral. And then we can calculate it using the old calculus rules. What is also interesting is that the converse is not true. A counterexample is the Dirichlet function, which is the indicator of the rationals, let's say, between A and B. Okay. Let's talk about it. Let's talk about it. Okay? So what is that? It's the indicator of rationals intersected A to B. Okay? Rationals, what kind of a set is that? Rationals countable. Countable means what? It is also Borel, right? So any countable set is a Borel set, just consisting of singletons. Therefore, it's a measurable set. It's a countable set. It's a measurable set. It's a Borel set. Indicator of a Borel set is a measurable function, right? So this is just, by step 1, Lebesgue integrable. What is the integral of this with respect to Lebesgue measure? The Lebesgue measure of Q intersected A to B. And what is that? What is the Lebesgue measure of Q intersected A to B? How many points are there in Q intersection A to B? Okay, let's write. So note Q intersection A to B is countable. So it is Borel. So indicator of Q intersection A to B is measurable. And its integral with respect to Lebesgue measure is the Lebesgue measure of Q intersection A to B. Now, Q intersection A to B is a countable set, like Q1, Q2. So you can write it as Lebesgue measure at Q1, Lebesgue measure at Q2, etc., and each are 0. So it's just 0. Integral is just 0, right? You have a function on a countable set. And the Lebesgue measure of the countable set is always 0. So it is automatically 0. The integral is 0. But the point was that it is Lebesgue integrable. However, indicator Q intersection A to B is not Riemann integrable. Because it is discontinuous everywhere on A to B. So its set of discontinuities is this full set A to B, which is non-zero. So I'm using this characterization. The set of discontinuities has non-zero Lebesgue measure. Therefore, it is not Riemann integrable. No, we're not going to prove it. We're not going to prove it. And I didn't want to check it using this classical definition of Riemann integrability because it is a bit boring, right? It is a bit boring. And slightly unrelated. Of course, it's an important connection, but I just wanted to say it as a fact. Okay? The fact is that if f is Riemann integrable, then it is also Lebesgue integrable, and the integrals coincide. Therefore, you can use your knowledge about calculus. That's why at the beginning of the course I said you should know calculus. You should know integration by parts and things like that, because now whenever you have an integral with respect to the Lebesgue measure, you can convert it to an integral with respect to like the usual Riemann integral and calculate it using, for instance, integration by parts, substitution methods, etc., etc. Okay. What's going to be more surprising is that we can even convert some integrals with respect to more abstract measures to integrals with respect to Lebesgue measure. So we will even have another equality here next week, where we will start with an abstract measure here, and we're going to convert it to the integral with respect to the Lebesgue measure. That's going to be more interesting. So even if you don't start with the Lebesgue measure, but you have some real valued random variable, you can pass to integrals like this, Riemann integral. Okay? So any questions? These are all important examples. And but for now, our abilities to calculate things is very limited, right? Because so far we haven't talked about distributions of random variables. So next week, we're going to introduce this notion of distribution. And then if you assume some distribution, you have a better ability to calculate stuff like expectations, variances, etc. Okay? Should I keep this board? Maybe I should. Okay, maybe, okay, over there, I will continue. So that is it about examples. So in the rest of the lecture, I'd like to talk about some nice property of integral with you. Okay? And this is called insensitivity. What is insensitivity? Insensitivity means, in quotations, null sets don't matter much in measure or probability theories. What is null set? Null set is a set with measure 0. Okay? So if you're on R2 and you use Lebesgue measure, okay, and you have a set like this, let's call it A. Okay? It's a curve on R2. What is the area of this curve? What is, not length, area. What is the area of this curve? Just 0, right? It has no area. So if you have a function defined on this set, something like this, and maybe the function is defined on the full set R2, okay? Let's call it x, okay? The thing is that if mu a is 0, integrate whatever function on a, you get 0. So no matter how complicated your function is, if you integrate it on a set of measures 0, its integral will be 0. Okay? This is insensitivity. So let's state it as a theorem. X is just measurable, omega to r bar. And A is a set, measurable set. Now, we should prove it. And the proof will be, again, fun, because we're going to use our usual path. Indicators, simple functions, positive functions, so on. So if X is indicator A, well, I should say B now, because A is a fixed set here. Let's use B. So what is the integral of X over A, over this fixed set? Well, X is indicator B d mu over A. So this is indicator B times indicator A, right? Which is indicator A intersection B. So it is indeed mu of A intersection B. So what is mu of A intersection B? If mu of A is 0, mu of A intersection B is also 0, right? Because it's a subset of it. So this is also 0. So the integral is 0. If you have B1, A, B1, up to Bm, indicator Bm, and you'd like to integrate x d mu over a, what is it? Well, you can write it as B1 indicator A1, A intersection B1, BM indicator A intersection BM, and this is going to give you B1 mu A intersection B1, and BM mu A intersection BM. Therefore, these are all zeros. So again, the integral is 0. OK, I'm not going to do the rest. So if x is positive, again, check that x d mu is 0 over a. And if x is just general, OK, numerical, then again, check x d mu is 0. It's going to be defined as limit of zeros, so this is going to be 0. And this is going to be x plus minus x minus. Each of them is 0, therefore the difference is 0. So the function itself doesn't matter. If you integrate on a null set, you're going to get an integral equal to 0. Using this, you can prove many other nice results. Which I'm going to write down as facts or exercises. So if you have x and y that are positive measurable, and x equals y, mu almost everywhere. What does that mean, mu almost everywhere? The set on which they are not equal is null. Okay? Almost everywhere means this happens. This does not happen on a null set. Otherwise, it always happens. So if you have two functions that are equal almost everywhere, then their integrals are equal. So this difference between x and y, which only matters on a null set, does not affect the values of the integrals. So if x and y were completely identical, their integrals would be identical. But if they differ on a null set, we still have the result. Integral is insensitive. That's why. So another exercise is if you have x positive measurable and the integral of this is 0, then you can say x is 0 almost everywhere. This is also a very natural result. First of all, it's a positive function, right? It's a positive function, so its integral is also positive. What we're assuming is that the integral is even 0. So this means the function itself must be 0, but it is OK if it is non-zero on a set of measure 0. So if x were completely 0, you would believe that the integral is also 0. And now we're assuming that the integral of a positive function is 0. This implies that x is 0 almost everywhere. So because if it is non-zero on a null set, its integral on that null set will just be 0. So the function can be free on a set of measure 0. Otherwise, it should behave nicely. It is even if and only if, right? The opposite part is kind of obvious, right? You have a 0 function, so its integral is 0. What else can you do with this insensitivity? You can write down the almost everywhere version of monotone convergence theorem, and also for dominated convergence, Fatou's lemma, etc. So here's how. So let's write down monotone convergence theorem. What does that say? So xn is positive, first of all. So now I make it almost everywhere. What does it say? Xn plus 1 is greater than xn. So this is an increasing sequence. I make it almost everywhere for all n. Then the result doesn't change. But I should write it in the following way. So let me write it this way. Then the limit exists almost everywhere. And for definiteness, just set limit xn of omega to be 0 if the limit does not exist at omega. You can still make it a well-defined function on omegas at which the limit does not exist. At the end of the day, the set of all such omegas is a null set, so we don't care. We have the integral of the limit is equal to the limit of the integrals. Same conclusion. You can also have almost everywhere versions of dominated convergence, Fatu, reverse Fatu, etc., etc. Questions about insensitivity? So is the idea clear behind insensitivity? So if you have a set that does not really matter with 0 measure, whatever you do on it doesn't matter for your end results, meaning that for your integrals. Okay? You satisfy the criteria of monotone convergence theorem almost everywhere. Namely, the functions may be very crazy on a set of measure 0, but this does not affect anything in the end result. You still have integral of limits equal to limit of integrals. Okay? So I'd like to finish the day by a nice result, characterization of integral, which we will maybe use once or twice. So it is kind of secondary importance, but still it's a nice result. So let's say you have the collection of all measurable functions that are positive. We also have, okay, measurable and positive, okay. L0 of, with values in the positive part, okay. So if a measure mu is given, then define L of x as integral of x d mu. What am I doing here? I'm defining integral as a functional. As a functional. Functional meaning that it is a function whose input is a function. Okay? And this is always positive valued. So L is defined on this set of random variables, mapping into positive extended real line. Satisfies A, L of 0 is 0. B, L of ax plus by is A L of x plus B Ly, where A, B are positive and xy are in L0. C, if you have x1, x2, etc., converging to x in L0, then L of x1 is less than L of x2, and they converge to L of x. So this is nullity, this is linearity, and this is monotone convergence. I just rewrote what we already know, but I rewrote them without referring to mu. So I defined a functional L, and I just replaced integrals with this L. So there is nothing to show about this. What is nice is that this theorem, sometimes called the Daniel-Stone theorem, so if L is any functional, is a functional satisfying ABC, then there exists a unique measure mu such that L is indeed the integral of x with respect to mu for all x. So in other words, if you have a functional which is linear and satisfies the monotone convergence type property, make sure it's an integral. We know it is an integral with respect to some measure. Okay? So start with some functional. You don't know if it is an integral. So if it satisfies those three properties, it is an integral with respect to some measure. So I'm going to skip the proof, but the idea is very simple. Just define mu of A as L of indicator A, then show mu is a measure. First show mu is a measure, then show it is an integral, L is an integral, and show if mu tilde is another such measure, then mu and mu tilde are equal. And that's the uniqueness part. So it's just a sketch of proof. And all you need to do is to extract a measure out of this functional. And if you're given a functional, you can just use the values of it at indicator functions, right? At indicator functions. So now this is a function of a set for each A. So the program is to show that it is a measure, then check that it is L is an integral with respect to measure mu, and finally show that you can only have one such measure. So if mu tilde is another measure satisfying this property, then you should show that mu equals mu tilde. Okay? So in fact, linearity and monotonicity plus monotone convergence were the correct properties to focus on. In fact, they characterize what an integral means. Okay? So let's finish the day, and next week we're going to talk about distributions.